It's 2:47 in the afternoon. The temperature outside has not dropped below 38 degrees since morning. Inside a windowless facility, rows of monitoring stations stretch into the distance. Each screen pulses with live data. The numbers climbing on the demand graph are higher than anything the operators have recorded on this day of the year before. The grid is carrying more electricity right now than at any point in the last decade. The margin between stable and catastrophic is measured in fractions of a percent. Somewhere in the transmission network, a long stretch of steel cable has been carrying current all morning under a sun intense enough to expand the metal by several centimeters. The sag is within tolerance, but only just. The current flowing through that cable is approaching the thermal limit. A single degree more and the protection relay will make its own decision. It will not wait for a human command. At 2:51 p.m. the relay trips. The line is gone. The remaining network absorbs the load in milliseconds. This is the moment every grid operator prepares for and hopes never comes on a record demand afternoon. With one line gone, every other path through the network is now carrying more current than it was designed to handle for extended periods. The system has not failed, but it is no longer comfortable. A second trip on any adjacent line now would begin a cascade. The operator has a 90-second window to reroute generation before the automatic systems begin shedding load. 90 seconds is both an eternity and nothing at all. In that window, the operator must find which generating stations have room to ramp output, coordinate with balancing authorities in 2 neighbouring regions, and verify that the new routing will not push any other line over its emergency rating. The commands go out. One by one, the generator outputs begin to shift. The overloaded lines ease, degree by degree, towards safety. 73 seconds after the trip, the last overloaded transmission line drops back inside its emergency rating. Outside, in every city and suburb within range of that network, nothing happened. The air conditioners kept running. The hospital monitors kept tracing their quiet lines. The refrigerators kept their temperature. Not one person noticed. The system absorbed the failure and corrected itself in the time it takes to read this sentence aloud. That is what the grid does, every hour of every day, without anyone watching. The electric grid is not a single thing. It is not a wire that runs from a power plant to your home. It is a living, breathing machine built by hundreds of thousands of people over more than a century, constantly balanced, constantly corrected, carrying enough energy at any moment to power every city on Earth simultaneously. Engineers who study it call it the most complex machine humanity has ever built. Tonight, we're going to follow it from the moment electricity is born to the instant it crosses your threshold. By the time you finish watching this, you will have a different relationship with every light switch in your home. Not because the grid is frightening. It is, in fact, one of the most reliable systems ever engineered, but because the quiet confidence of that reliability is earned, every second, by a chain of physics and infrastructure so intricate that most of the people who depend on it most have never thought to ask how it works. Let us begin at the beginning. Electricity does not exist in nature waiting to be collected. It must be made continuously at scale. Every watt of electricity flowing through the grid right now was generated within the last fraction of a second. Unlike water, which can be stored in a reservoir, or fuel, which can sit in a tank, electricity must be produced and consumed at the same instant. The entire generating capacity of the grid is running in perfect synchrony with the entire consuming load, balanced to within fractions of a hertz right now, without pause. This is the central engineering challenge of the modern world. The fuel that powers most of this generation is invisible. Natural gas burning inside turbines, uranium releasing heat inside reactor vessels, wind spinning blades on offshore towers, sunlight striking photovoltaic cells across desert plains. Each source converts energy into mechanical rotation or direct current, and that motion or current is then transformed into the alternating current that the grid runs on. The method differs by source, but the destination is always the same: the spinning magnetic fields of a generator. Inside a generator, a rotating magnetic field passes across copper windings. The changing magnetic flux induces a voltage in those windings, and because the rotor is spinning at a precise constant rate, the voltage alternates in a smooth sinusoidal wave exactly 60 times per second. That 60 Hz rhythm is the heartbeat of the North American grid. Every generator in the network, from the largest nuclear plant to the smallest peaker turbine, spins at exactly the same frequency. They are all, in a real physical sense, coupled to one another. The output voltage leaving a large generator is immense, but to travel hundreds of miles, it must rise higher. The step-up transformer at the power plant is one of the most important and least celebrated pieces of equipment in civilization. Its job is to take the generator's output, typically between 10,000 and 25,000 volts, and raise its transmission voltage, which may reach 765,000 volts on the largest lines. The physics is simple. Higher voltage means lower current for the same amount of power, and lower current means less energy lost to resistance in the wire. Without this step, a power plant 50 miles from a city would lose most of its output to heat before the electricity ever arrived. The transmission lines that carry this high voltage current are the arteries of the grid. In the United States alone, there are more than 700,000 miles of them. Most are made of aluminum reinforced with a steel core, light enough to sag gracefully between towers hundreds of meters apart and conductive enough to move enormous amounts of power with acceptable losses. The towers that hold them rise anywhere from 20 to 60 meters, spaced to keep the lines safely clear of trees, buildings, and anything else that might interrupt their path. The grid moves power invisibly and silently. Nothing vibrates, nothing glows, nothing announces itself. The towers stand in fields and along highways, and most people drive past them for decades without once wondering what they carry. Inside those cables, electrons are flowing at nearly the speed of light, carrying the energy that will arrive at a socket in a home within fractions of a second. The invisibility is by design. The grid works best when it is never noticed. The North American grid is not one grid but three. Eastern interconnection covers most of the continent east of the Rocky Mountains. The Western interconnection covers everything west of them, from the Canadian border to the tip of Baja California. And the third, smaller grid covers one state in the south, isolated from the others by deliberate political decision. Each of these is electrically independent, connected to its neighbours only by high-voltage direct current links that convert AC to DC for crossing the seam, then convert it back. This isolation is not an accident. The three-grid design was an engineering decision made generations ago and never fully revisited. Each interconnection can absorb failures internally without immediately threatening the others. But it also means that a region with surplus power cannot always easily share it with a region that is short. On the hottest summer days, when one interconnection is straining, the next one over may have power to spare but no simple way to send it across the boundary. The DC ties that bridge the seams are expensive, heavily loaded, and far too few. There are more than 11,000 power plants feeding the North American grid at this moment. They range from massive baseload facilities that run continuously for months, supplying power around the clock, regardless of demand, to small peaker plants that sit idle most of the year and fire only on the hottest afternoons when the last increment of capacity is needed. The baseload plants provide the steady foundation. The peakers fill the peaks. In between, mid-merit generators ramp up and down throughout the day, following the curve of demand as it rises in the morning and falls again after midnight. The entire fleet is choreographed by software that places bids and dispatches generation in real time. The system dispatches this generation portfolio in a market that runs every 5 minutes. Generators submit offers stating the price at which they are willing to run. The balancing authority accepts the cheapest bids first and works up the cost curve until supply meets forecast demand. This auction runs continuously 24 hours a day, every day of the year. By morning, the dispatch schedule for the following day is already set, hour by hour, subject to revision every 5 minutes as reality diverges from the forecast. The transmission system that carries this dispatched power is operated in real time by control centres that monitor thousands of data points simultaneously. Every line, every transformer, every generator output is measured and updated multiple times per second. Operators can see, at a glance, the loading on every major element in their region. They can run security studies. Mathematical simulations of what happens if any single element fails. And they do, constantly during every operating hour. The system must remain stable, not just under current conditions, but under the worst single failure that could occur right now. This is the N-1 criterion. The grid must survive the sudden loss of any single element without cascading. The N-1 criterion is the foundational safety rule of grid operation. At every moment, the system must be able to withstand the sudden loss of any one line, any one transformer, any one generator, and continue serving all load without any other element exceeding its emergency rating. This means the grid is never running at its theoretical maximum. It always keeps something in reserve, always operates with margin. When that margin erodes, as it did on our record heatwave afternoon, the operators have a narrow window to restore it before the system becomes vulnerable to the next event. Grid operators train for years to read the signs of approaching instability and respond before the automatic systems take over. Automation is fast. Relay responses happen in milliseconds. But operators are the last line of judgment for anything that falls outside the preloaded scenarios. A skilled control room operator who has worked a network for a decade carries a mental model of it that no computer fully replicates. They know which lines tend to run hot in certain wind conditions. They know which generators take longer than expected to respond. That knowledge is not written down anywhere. As demand climbed through the afternoon of our heatwave, that knowledge was exactly what was needed. The operator who cleared the contingency in 73 seconds did so partly because of procedure and partly because of memory. A recollection of a similar event 3 summers earlier on a different line with a similar pattern of loading. The grid is not just steel and copper. It is the accumulated institutional knowledge of the people who run it. Outside the control room, the afternoon continued. Children came home from school. Factories ran their evening shift. Hospitals began their overnight preparation. All of it powered by a machine that had just absorbed a serious contingency and returned to stability in the time between 2 heartbeats. The grid does not ask for acknowledgement. It simply continues. To understand why this reliability is so remarkable, we need to go deeper into the physics. The grid does not just carry electricity. It maintains a precise agreement, enforced by the laws of physics between every generator and every load connected to it. Disrupting that agreement, even briefly, sends shockwaves through the entire interconnected system. The story of how the grid maintains that agreement, every hour in all weather, across 3,000 miles, is the story we are going to follow through the rest of this video. The physics that govern the grid were worked out in the 1880s. They have never been revised. Alternating current, the kind the grid runs on, is a voltage that changes direction 60 times per second. This oscillation is not an accident or a compromise. It is the very property that makes the transformer possible, and the transformer is what makes long-distance transmission practical. A transformer only works with changing magnetic flux, and changing flux require alternating current. The entire architecture of the modern grid, high voltage transmission, local distribution, the ability to move power across continents, is built on the alternating current principle discovered and promoted in the final decade of the 19th century. The 60 Hz frequency is the shared pulse of the grid. Every generator connected to the North American system produces current that completes 60 cycles per second. If demand increases and generators cannot immediately supply more power, the frequency begins to drop. The generators slow slightly, like any machine under greater load. If demand decreases, the frequency rises. Control systems on every generator monitor this frequency constantly and adjust output to hold it within a few hundredths of a hertz of the target. This collective response is called primary frequency response, and it is automatic, instantaneous, and essential. If frequency falls too far, below about 59.5 Hz, automatic under-frequency relays begin shedding load. This is the grid's emergency self-protection, deliberately cutting power to some areas to preserve power everywhere else. The alternative is a full blackout, which is far worse and far harder to recover from. A controlled load shed is a surgical intervention. An uncontrolled cascade is the grid equivalent of cardiac arrest. The frequency response of the grid is not managed by any single authority. It is an emergent property of the entire interconnected system. Every large generator with governor control participates automatically. Every inverter-based resource, solar, wind, battery storage, can be programmed to participate. The result is a distributed control system of enormous scale, operating without central coordination, responding to the collective imbalance of the entire network in the same instant. Beyond primary response, the grid uses a second layer of control called automatic generation control. This software, running in every balancing authority's control center, monitors the frequency and the net flows across interconnections and sends minute-by-minute commands to generators to hold the system exactly on target. It is the slow response correction layer, operating on timescales of seconds to minutes, smoothing out the residuals that primary response alone cannot eliminate. Without it, frequency would drift and the grid would become progressively harder to keep stable. The transmission network carries this carefully balanced power across distances that would have seemed impossible a century ago. High voltage transmission is a study in the management of extremes, the voltages involved. Up to 765,000 volts on the largest lines are high enough to arc through several meters of air. The towers that hold these lines must be engineered to withstand not just the weight of the conductors, but the enormous mechanical tension of long spans in high wind, the differential expansion of metal across temperature ranges spanning over 100 degrees, and the occasional impact of ice loading that can add tons of weight to a single span in a single night. The conductor itself is a marvel of materials engineering. The outer layers are aluminum, lightweight and highly conductive. The core is steel, strong enough to bear the mechanical tension of the span. In some modern designs, the core is made from a composite material lighter than steel and stronger, allowing longer spans between towers, which reduces the number of structures needed and cuts both cost and visual impact. The conductor hangs in a precise catenary curve between towers, its lowest point calculated to maintain the required clearance from ground at the highest temperature the line may experience. Every transmission line has a thermal rating, the maximum current it can carry without heating the conductor enough to sag dangerously. This rating is not fixed, it varies with ambient temperature, wind speed and solar radiation. A line that can carry 1000 amperes on a cool, windy night may be limited to 700 on a still summer afternoon. Dynamic line rating systems, increasingly deployed on critical corridors, measure these conditions in real time and adjust the allowed loading accordingly, sometimes revealing that a line has more capacity than its static rating suggests, and sometimes confirming that it has less. Scattered along every transmission line are protection relays, devices that measure the electrical conditions on the line and disconnect it automatically if they detect a fault. A fault is any condition where current is flowing somewhere it should not. A tree branch touching a conductor, lightning striking a tower, a conductor damaged by ice. The relay identifies the fault within cycles, fractions of a second, and opens the circuit breakers at both ends of the affected section. The line is de-energized before a human being has even had time to register that something happened. The circuit breaker that performs this isolation is itself a piece of extraordinary engineering. At transmission voltages, breaking a current of thousands of amperes creates an arc, a sustained electrical discharge across the opening contacts. That can burn for as long as the voltage sustains it. Modern circuit breakers use pressurized sulfur hexafluoride gas to quench this arc in milliseconds. The gas is an extraordinary insulator and arc suppressant. The breaker operates, the arc forms, the gas absorbs it, and the circuit is open. The whole sequence takes less than 1/10 of a second. After transmission, the voltage must come down to safe levels. The substation is precisely where that transformation happens. The transmission substation is where the pathway from generation to use changes character. The incoming high voltage, perhaps 345,000 volts, is stepped down to subtransmission voltage, perhaps 69,000 volts, by large power transformers. The substation also connects multiple lines, allowing power to be rerouted between paths, and houses the switching equipment and protection systems needed to isolate any section for maintenance or fault clearing. A major substation may cost hundreds of millions to build and take years to permit. It is, in a very real sense, a piece of critical national infrastructure. The large power transformer at the heart of a substation is among the most difficult items in the grid to replace. A major transformer for a high voltage substation may weigh over 400 tons and require a specially built rail car or heavy-haul truck convoy to transport. It may take 2 years to manufacture and deliver. There are only a handful of factories in the world capable of building the largest units. Utilities maintain strategic spare transformers for exactly this reason, because losing a major transformer to a fault or a physical attack without a spare can mean months without full capacity. From the substation, electricity travels on subtransmission lines to smaller distribution substations scattered through towns and cities. These smaller substations step the voltage down again to the levels used on distribution lines, typically between 4,000 and 35,000 volts. From these distribution substations, the familiar poles and wires of the neighbourhood grid carry power through residential streets, past front yards and along back alleys, to the final transformer that will bring the voltage to the 120 and 240 volts used inside homes. The distribution network is the least glamorous part of the grid and the part most people are most familiar with, even if they do not know its name. The wooden poles, the clusters of wires at intersections, the cylindrical grey cans hanging from cross arms. These are distribution transformers, each one serving a handful of homes. Most were installed decades ago. Many are operating well past their original design life. The distribution network represents the largest maintenance challenge and the largest investment need in the entire electricity system. The voltage inside your home, 120 volts in North America, is the endpoint of a journey that began at 765,000 volts or higher and was stepped down in at least 3 stages. The ratio of transformation across that journey is roughly 6,000 to 1. That ratio represents not just a change in numbers, but a complete change in the physical character of the electricity. From a current that would arc through meters of open air to one safe enough to power a lamp or charge a phone. The meter outside your home is the last measuring point on this chain. It records every watt-hour that crosses the threshold between the utility's distribution network and your internal wiring. Behind it, your wiring carries that power to every outlet, every switch, every appliance. The meter itself is increasingly a two-way device, capable of reading export as well as import. Because the grid is changing, and the direction of power flow is no longer as simple as it once was. Renewable generation, principally wind and solar, has transformed the grid's operating challenge in the last 15 years. Both sources are intermittent. The sun does not shine at night. The wind does not blow on demand. A grid dominated by fossil fuels could be dispatched, tell a generator to run more, it runs more. A grid with a large fraction of renewables must work around the variability of sources that respond to the weather, not the market. The challenge of integrating large amounts of renewable generation is, at its core, a challenge of real-time balancing on a far more complex and volatile supply curve than the grid was originally designed for. Battery storage is the technology the grid has been waiting for. It arrived just in time. Grid-scale battery storage is now deployed in gigawatt-hours across the North American system. These installations charge when power is cheap and abundant, often in the middle of the day when solar generation is at its peak, and discharge when demand is high and supply is short. They can respond to frequency deviations in milliseconds faster than any thermal generator can ramp. They are, in a real sense, the first technology in the grid's history that can store the surplus of one moment and return it in the deficit of the next at meaningful scale. The integration of storage and renewables has driven the rapid development of grid management software far more sophisticated than the systems of a decade ago. Modern energy management systems process thousands of data streams simultaneously, running state estimation algorithms that construct a mathematical model of the entire network in real time, updated every few seconds. From this model, they identify vulnerabilities, predict imbalances, and generate dispatch recommendations that operators can accept or modify. The grid that exists today runs on far more computation than the grid of 20 years ago, and the trend is accelerating. In 2026, artificial intelligence is beginning to play a meaningful role in grid operations. Machine learning models trained on years of operating history can forecast demand more accurately than traditional statistical methods, particularly at the distribution level, where individual behavior creates highly variable loads. They can predict the output of wind and solar farms hours in advance with greater precision than meteorological models alone. And they can identify anomalous patterns in the sensor data, patterns that might indicate equipment degrading toward failure before any alarm has triggered. The physical sensors feeding these systems have also become extraordinarily dense. Phasor measurement units, now deployed by the thousands across the transmission network, measure the voltage and current at their location with extreme precision and timestamp every reading against a GPS clock. This allows the control system to construct a picture of the entire network state at a given moment with a resolution that was unachievable a generation ago. The grid has always had sensors, but the new sensors tell a fundamentally different kind of story. Not just how much power is flowing, but how the waves of electrical energy are propagating and interfering across the entire interconnection. This depth of measurement has made the grid more observable than ever before. But observation alone does not guarantee stability. The data must be acted on, quickly, by systems and operators who can translate a pattern in the numbers into a real intervention on physical equipment. The gap between knowing and acting is where the grid remains most human and most vulnerable. Systems can see almost everything. Acting fast enough still depends, at critical moments, on people. Return, for a moment, to the afternoon of our heatwave. We are now 48 hours into the 90-second window that defined that day. The operator made the right calls. Cascade did not happen, but somewhere the analysis of that event is being written up. The post-contingency review that every balancing authority conducts after any significant event. That report will ask what happened, why it happened, and what would have happened if the response had been 3 seconds slower. The grid learns from its near misses. The post-event report will also ask a harder question. How close was this? The margin between the event that occurred and the cascade that did not will be measured precisely. If the margin is large, operations continue with minor adjustments. If the margin is small. If the review shows that a few more seconds of hesitation or a slightly different initial state would have led to widespread outages, then something more substantial changes. New procedures are written. New equipment is ordered. The grid absorbs the near miss and tries to make it less likely next time. This continuous learning process is one of the reasons the grid has become more reliable over time, even as it has become more complex. Each major event, each blackout, each near miss, each unusual operating condition contributes to a body of knowledge that is incorporated into operating procedures, training scenarios, and protective relay settings. The grid that exists today is the accumulated result of 100 years of failure analysis. Every safety feature it has exists because something, at some point, went wrong without it. What comes next in the technical story is the grid's ongoing transformation. The system being operated today is not the system that will be operated in 10 years. The drivers of change are well understood: more renewable generation, more distributed resources, more electrification of transport and heating, and the fundamental challenge of building new transmission in an era where permitting and public opposition can delay a single line for a decade. The technical challenges ahead are significant. The grid's engineers are already working on them. The expansion of electric vehicle charging is one of the most immediate pressures on the distribution network. A single fast charger can draw as much power as several homes simultaneously. A neighbourhood where half the residents charge their vehicles at the same time in the evening creates a load spike that the existing distribution infrastructure may not be designed to handle. Utilities are investing in distribution upgrades and smart charging systems that shift charging to off-peak hours, but the deployment of these systems is running a close race with the adoption of the vehicles they are meant to accommodate. The heating sector is undergoing a parallel electrification. Heat pumps, devices that move heat from outside air into a building, even in cold climates, are increasingly replacing gas furnaces and boilers as the decarbonisation of heating accelerates. A heat pump draws 2 to 4 times less energy than a direct electric heater for the same amount of warmth, which makes them the preferred technology. But they still draw significant power, and their aggregate effect on winter peak demand, particularly in cold regions transitioning rapidly from gas, is one of the grid's planning challenges for the coming decade. A fundamental tool for managing all of this growing and shifting load is a concept called demand response, the ability to reduce or shift electricity consumption in response to grid conditions or price signals. Smart thermostats that pre-cool homes before a heat wave and then allow temperature to drift during peak hours are a form of demand response. Industrial facilities that agree to curtail their processes for a fee during grid stress events are another. In aggregate, demand response represents a significant and flexible resource that does not require building a single new power plant. Demand response is one of several technologies that together constitute the smart grid, a term that covers any use of digital communication and control to make the electricity system more efficient, more reliable, or more flexible. The smart grid is not a single system. It is a loose collection of technologies and standards being deployed at different rates and with different architectures by different utilities. Some of the most impactful smart grid investments are also the least visible. Advanced metering infrastructure that allows two-way communication between the utility and every meter, enabling the grid to know in near real time exactly where power is being consumed. As we leave Act 2 and prepare to look at where this system breaks, it is worth pausing on what has been built. The electric grid is a machine with no off switch, no standby mode and no reset button. It has been running continuously since before the First World War in some regions. It has survived storms, wars, economic crises and technological transformations that would have destroyed most human institutions. It is right now, delivering more energy with more reliability and less carbon intensity than at any point in its history. That is an extraordinary achievement. It is also not enough. Every grid operator carries a list of scenarios they hope never to face. Some of those scenarios have already happened. The most catastrophic grid failures in history share a common structure: an initial contingency, a delayed or inadequate response, and a cascade of automatic actions that each make the situation worse. The sequence can unfold in minutes. A system that was supplying tens of millions of customers can be completely de-energized before any human operator has fully understood what is happening. The physics do not wait for comprehension. They proceed according to their own schedule. The cascade mechanism works as follows. When a major element trips, power that was flowing through it redistributes to adjacent paths. Those paths were already loaded. The additional power raises their current, heats their conductors, and reduces their thermal margin, if conditions are right. If the grid was already operating near its limits, if the automatic responses are slow or insufficient, one of those adjacent elements will reach its own protection limit and trip, and then the redistribution happens again to the remaining paths. And again. Each trip is faster than the last. A cascade blackout is one of the most difficult events to recover from in all of engineering. The grid cannot simply be switched back on. Each generator that has been disconnected must be restarted, a process that takes time and requires a source of power to begin with. The system must be rebuilt piece by piece, island by island, carefully matching generation and load in each isolated section before connecting sections together. A full restoration from a major cascade can take days. In winter, days without power can mean frozen pipes, failed heating systems, and serious danger to vulnerable people. The most significant cascade blackout in North American history, in the early 2000s, began with a software alarm system that had stopped functioning correctly hours before the first fault. Operators were flying blind. The alarms that should have alerted them to growing problems were silent. A series of line trips, each individually manageable, cascaded in the absence of coordinated response into a blackout affecting over 50 million people. The restoration took 4 days. The investigation found dozens of contributing factors, but the root cause was the silence of alarms that should have been heard. The reforms that followed that event fundamentally changed how the grid is operated in North America. New reliability standards were written and made legally enforceable. New requirements for real-time situational awareness were imposed on all control room operators. The concept of wide area monitoring, using the phaser measurement units we encountered earlier, was accelerated. The grid after that blackout was not just repaired, it was, in important ways, redesigned. The next cascade would be harder to start and easier to stop. But the grid faces threats that the post-blackout reforms were not designed for. Cybersecurity is now one of the most serious concerns in grid operations. The digital systems that enable smart grid monitoring and control also create attack surfaces that did not exist in an analog grid. Industrial control systems that were once air-gapped from external networks are now connected to corporate networks, to cloud services, to the wider internet. Each connection that enables efficiency also enables intrusion. Cyber incidents targeting energy infrastructure have increased sharply in frequency and sophistication through the 2020s. The most concerning attacks are not those that cause immediate disruption, which are quickly detected and responded to, but those that establish persistent access, study the system's operating patterns over months, and position themselves to cause maximum damage at a moment of their choosing. The defenders are aware of this. The grid's cybersecurity posture has hardened significantly, but the attackers have also grown more capable. Climate change is reshaping every physical threat the grid must now withstand. The old calculations are being revised. The grid was designed to handle the weather of the 20th century. The temperature extremes, the storm intensities, the ice loading events that were used as design inputs for towers and conductors were based on historical records. As the climate shifts, those historical records no longer reliably represent what the infrastructure will face. The once-in-a-century winter storm is occurring on a shorter return period. The record heat summer of a decade ago is now the normal summer. Equipment designed for conditions that no longer define the range of experience is exposed to conditions it was not designed for. The storm that creates the most immediate grid damage is the ice storm. Ice accumulates on conductors and towers at a rate that can exceed the structural design loading within hours. When conductors fail, they take the tower with them. When towers fail, they take the next tower with them. A single severe ice storm can destroy hundreds of kilometers of transmission line in a night, creating damage that takes weeks or months to repair. The most costly and longest grid restoration events in North American history have been driven by ice, not by any technological failure. Wildfires present a different but equally serious threat in the western part of the continent. High voltage lines in fire-prone terrain must be de-energized when conditions create ignition risk. A management practice that prevents utility-caused fires, but also removes power from the very areas most in need of electricity for cooling medical equipment and emergency communication during extreme heat events. The tension between fire safety and power access is one of the most difficult operational challenges facing Western utilities today. The aging of the transmission and distribution network is another source of compounding risk. A substantial portion of the grid's infrastructure was built in the 1950s and 1960s, designed for a 50-year service life. It is still in service. Transformers show signs of insulation degradation. Poles and distribution circuits are at the end of their structural service. Underground cable in urban areas, installed generations ago in materials no longer manufactured, is failing with increasing frequency. The replacement rate has been accelerating, but the backlog is enormous. Against this backdrop of accumulating risk, the grid's operators and planners are working on the infrastructure of the future. The most important single investment is new transmission. More transmission capacity means more ability to move surplus renewable generation from where it is abundant to where it is needed. It means more redundancy in the event of failure. It means the ability to balance larger areas against one another, smoothing the variability of wind and solar across geography. The economic and reliability case for new transmission is strong. The permitting challenge is severe. A new high-voltage transmission line in the United States may take 15 to 20 years from initial study to energization, with the majority of that time spent permitting, environmental review, and negotiating rights-of-way through private land. The technical work of designing and building the line takes 3 to 5 years. The rest is process. Grid planners have been calling for a streamlining of transmission permitting for decades. The gap between the transmission the grid needs and the transmission being built remains one of the most important and least discussed constraints on the energy transition. The future of the grid is not only about more wires, it is about a fundamentally different kind of network. The grid of 2030 will carry a larger fraction of its power on high-voltage direct current lines than the grid of today. DC transmission has significant advantages over AC for very long distances. No reactive power losses, no synchronization requirements, the ability to control power flow precisely. Modern voltage source converter technology has removed the last major technical barriers to flexible DC grids. The economic barriers are coming down as the technology matures and production scales. The first true DC meshed networks are already being proposed and permitted in several regions. Superconducting cables. Conductors that carry electricity with zero resistance when cooled to cryogenic temperatures. Are moving from laboratory demonstration to initial commercial deployment. A superconducting cable can carry the same current as a conventional cable many times its cross-section. In dense urban environments, where underground conduit space is the critical constraint, superconducting cables could allow a radical increase in capacity through existing cable routes. The cooling infrastructure required is a challenge. The physics of zero resistance is extraordinary. Grid-scale storage beyond lithium-ion is also advancing. Flow batteries, which store energy in liquid electrolytes held in external tanks, offer duration advantages. They can be charged and discharged for longer periods than current lithium technology. Iron-air batteries, which oxidize and reduce iron to store and release energy, use one of the most abundant materials on Earth and are designed for multi-day storage. These technologies are not yet deployed at scale, but the trajectory of development suggests that within this decade, the grid will have access to storage options that fundamentally change its flexibility. The microgrid is another architectural element of the future grid. A microgrid is a local network that includes generation, storage, and load, and can operate either connected to the main grid or islanded from it. During an extended grid outage, a microgrid can continue to supply its local customers from its own resources. Hospitals, military installations, and critical facilities are increasingly adopting microgrid architectures precisely for this resilience property. At scale, a grid composed of many capable microgrids would be far more resilient to cascade failures than the current monolithic architecture. The idea of the distributed, intelligent grid, where generation and storage are embedded throughout the network and every node can both consume and supply, is not a new vision. It has been articulated by grid engineers for several decades. What has changed is that the enabling technologies, affordable solar, affordable batteries, power electronics capable of managing bidirectional flows, and communication systems capable of coordinating millions of independent resources, have all arrived in the same decade. The vision is becoming engineering. Artificial intelligence will accelerate this transition, the coordination of millions of distributed resources. Each one small, each one variable, each one with its own constraints and preferences. It is a problem of extraordinary combinatorial complexity. No human dispatcher can manage it. No deterministic algorithm can handle the full range of conditions. But machine learning systems trained on the patterns of distributed grids can learn to coordinate these resources in real time, using market signals, grid conditions, and weather forecasts as inputs. This is already working at modest scale. It will need to work at enormous scale within a decade. Now we return, at last, to the operator from our afternoon heatwave. The post-contingency review of that event was completed 2 weeks later. The analysis confirmed that the line trip was caused by contact with a tree that had grown into the conductor's sag zone during a period of record high temperatures. The vegetation management schedule for that corridor was updated. A dynamic line rating monitor was ordered for that section of line. The automatic response performed correctly. The operator's response time of 73 seconds was within the target window. The grid survived that afternoon, as it has survived 10,000 afternoons before it and will survive 10,000 more. Not because it is infallible. It is not. But because it has been built layer by layer, failure by failure, with a kind of institutional memory that makes it progressively more robust with each event it experiences and learns from. The machine does not stop improving just because it is already extraordinary. The operator who cleared the contingency that afternoon did not go home and think about it. This was not unusual. Grid operators handle multiple contingencies in a typical week. Most are small. A distribution fault here, a transmission element out for scheduled maintenance there. July heatwave event was notable but not exceptional. It was exactly the kind of event the operator had trained for, had run in simulation a dozen times, and had responded to with the quiet confidence that comes from years of exposure to the machine's rhythms. That quiet confidence is perhaps the grid's most important resource. The engineers who designed it, the operators who run it, the technicians who maintain it, they carry inside them a knowledge of this machine that cannot be fully transferred to any database or algorithm. It is embodied, procedural, experiential knowledge of the kind that accumulates only through sustained engagement with a complex, dynamic, unforgiving system. The machine's continuity depends on their continuity. The vision of the grid in 2030 is not a different machine. It is this machine, extended and deepened. More generation, more storage, more transmission, more sensing, more intelligence. The same principles of physics. The 60 Hz frequency, the transformer equation, the thermal rating of conductors will still govern it, the same fundamental challenge. Balancing supply and demand, moment by moment, across a network that spans a continent, will still define its daily operation. What will change is how precisely and flexibly that balance is maintained. The energy transition, in its most optimistic form, runs on the grid. Every electric vehicle that replaces a combustion engine, every heat pump that replaces a gas boiler, every industrial process that shifts from fossil fuel to electricity. All of it flows through the same wires that run down every street, past every home, in every city on the continent. The grid is not just the infrastructure of the electricity sector. It is becoming the infrastructure of the entire energy system. The stakes of getting it right are difficult to overstate. As darkness falls outside and the air finally begins to cool, the grid shifts its character. The peaker plants that ran hard through the afternoon begin to back down. The evening demand ramp fills the gap with a different mix of resources. More battery storage, more imports from neighbouring regions, less gas. The frequency is steady. The control room is quieter. The machine that has been working all day, without acknowledgement, continues, invisibly into the night. Tonight, while you sleep, the grid will continue. It will absorb the low-demand valley of the early morning hours, cutting generation to its minimum stable output. It will bring peaker units to standby, ready to respond in minutes if something unexpected happens. It will charge every battery storage installation on the system, filling them from the overnight surplus of renewable generation. And when the morning load begins its climb at 6 in the morning, the coffee makers, the water heaters, the first factories of the day, the grid will already be ready. Every light you switch on from this moment is part of a system of extraordinary complexity and extraordinary reliability, built over more than a century by hundreds of thousands of engineers, operators and technicians, maintained in real time by people in windowless control rooms you will never visit, and delivered to your socket through a chain of transformation and transmission that crosses hundreds of miles without a single human action. You will probably never think about this again, and that is exactly how it is supposed to work. The grid does not need to be noticed, it needs only to continue, and it does. What the grid needs from the rest of us is something different. It needs investment in the infrastructure that keeps it running and growing. It needs policies that make it possible to build new transmission in reasonable time. It needs a continued commitment to the workforce, the operators, the engineers, the technicians, who carry the institutional knowledge that no software has yet learned to replace. The machine is extraordinary, the people who run it are more so. Both deserve more attention than they receive. The next time the power goes out, for 30 seconds, for 30 minutes, for 3 days, you will have a clearer picture of what is being restored, not just the electricity, the agreement, the continuous, physics-governed agreement between every generator and every load in a network that spans a continent. When it breaks, it is extraordinary. When it holds, which is nearly always, it is more extraordinary still. There are megasystems more visible than the grid. A container ship on the horizon, a cargo aircraft overhead, a water treatment plant at the edge of town. These at least have a physical presence that announces itself. The grid is different. It is everywhere. It is always on, and it is almost entirely out of sight. The wires are so familiar that they have become invisible. The hum, if you hear it at all, is just background. The light is just light. But the invisibility is itself the achievement. The engineers who designed the grid's reliability standards, who wrote its operating procedures, who investigated its failures and built the reforms that followed. They were trying to build a system that would never need to be noticed. They succeeded more thoroughly than perhaps any other group of engineers in history. The grid's invisibility is the proof of its success. If this video has done its work, you now see what was always there. The transmission towers along the highway, the transformer on the corner pole, the meter on the side of the building. They are not background. They are the most complex machine humanity has built, running quietly at the edge of your attention, doing something astonishing every second of every day. The switch is waiting. The grid is ready. Which megasystem would you explore next? Leave it in the comments below. The grid is just one of dozens of invisible systems that keep the modern world running. Each one as deep, as intricate, and as quietly extraordinary as the machine we have followed tonight. Thank you for watching. Rest well. The grid has no beginning and no end. At any moment, a pulse of energy is leaving a generator somewhere on the continent and arriving at a load somewhere else. It has been this way since the first circuits were energized. The flow does not stop. It slows in the deep night and it rises with the sun, but it has not fully stopped in more than a century. Every contingency the grid faces is also a lesson. The relay that trips unexpectedly on a summer afternoon, the transformer that begins reading higher than normal dissolved gas, the distribution line that flickers during a thunderstorm. Each event is recorded, analysed, and added to the growing institutional knowledge of a machine that learns from everything that happens to it. The generator is the most fundamental object in the grid. It takes mechanical energy, the spin of a turbine, the turn of a rotor, and produces the electromagnetic force that moves electrons through every wire. Without the generator, there is no grid. The rest is infrastructure. The generator is the origin of everything that follows. The N-1 criterion will still govern the grid of 2035, just as it governs it today. The rule does not change because the technology around it changes. As long as the grid carries power that people depend on, it must be able to absorb the loss of any single element without widespread failure. That is not a technical standard, it is a social contract. The conductor carries its burden silently. There is no sound as it passes hundreds of megawatts across the landscape. No heat visible from the ground, no visible motion. Just the quiet transmission of enormous energy, constrained by physics, guided by engineering, watched over by relays that will act in milliseconds if anything goes wrong. The circuit breaker is the grid's immune system. It identifies a fault and isolates it before the damage can spread. A grid without reliable protection would be fragile. Every fault would cascade, every lightning strike would darken a city. The breaker absorbs the event and presents the rest of the network with a clean boundary. The grid continues. Renewable generation brought a new kind of uncertainty to the grid, not the uncertainty of a machine failing. Generators have always failed, but the uncertainty of a resource that varies with the weather and cannot be called up on demand. Learning to balance this variability is the defining engineering challenge of the energy transition. The algorithms that run in grid control centers in 2026 would be unrecognizable to the engineers who built the first computerized energy management systems in the 1970s. The fundamental problem they solve, balance supply and demand, is unchanged, but the number of variables, the speed of response, and the depth of prediction are entirely different. The phasor measurement unit network is the grid's nervous system. Thousands of sensors, each locked to the same GPS-derived clock, feeding a continuous picture of the entire interconnection into state estimators that run at a pace no previous generation of grid operators could have imagined. The grid sees itself more clearly than ever before. The operator who managed the heatwave contingency returned to that same control room the following morning. The grid had recharged overnight. The peaker plants were cooling. The frequency was steady at 60 hertz. From the outside, nothing had happened. That is the measure of a successful grid operation. The absence of catastrophe is the result of enormous work. The cascade failure is the grid's most feared event, not because it is common, it is rare, but because it reveals the depth of dependency. When the lights go out simultaneously across 100 million homes, the world that's been running invisibly becomes suddenly completely visible. We see in its absence what we had been taking for granted. The cascade teaches the same lesson every time it happens. The grid is not infinitely resilient. It depends on margins that can erode silently. It depends on systems that can fail quietly. And it depends on operators who must be ready to act correctly in the moments when everything else has already gone wrong. Margins matter. Readiness matters. Every major blackout in the grid's history produced reforms that made the next event harder to start. The pattern is consistent. Failure, investigation, new standards, new technology, new training. The grid does not learn from success. It learns from failure. Its reliability is not a steady state. It is the result of constantly recovering from near misses. The reforms following a major outage changed the grid for a generation. New protection settings, new operating procedures, new inter-utility communication protocols. The operators who were present at the event carry the memory of it for the rest of their careers. The written standards carry it long after those operators are gone. The climate changes the grid's design basis. Equipment rated for the weather of the last century is operating in the weather of this one. The engineering community is working through what that means. Higher conductor temperatures, more frequent ice storms, more extreme heat waves. The calculations are being redone. The designs are being revised. The permitting challenge for new transmission is not a technical problem. It is a governance problem. The grid needs new paths. The paths cross land that belongs to someone. Every parcel requires negotiation. Every negotiation takes time. The gap between the transmission the grid needs and the transmission being built grows while the process works through its stages. The direct current grid that engineers are beginning to build will carry power across longer distances with fewer losses. It will connect regions that have been electrically isolated for decades. It will make the energy transition faster and cheaper. It is, in a real sense, a second grid being built inside the first one. The distributed grid. Millions of small generators and storage units, each capable of operating independently, is both more resilient and more complex than the centralized grid it is gradually supplementing. Each node that can island from the main grid is also a node that must eventually reconnect. Coordination at scale is the challenge that defines the next chapter. The operator who cleared the heatwave contingency will retire one day. Their knowledge will be partially transferred through training programs and partially lost. The systems they learned on will be replaced by systems that are more automated and less forgiving of misunderstanding. Succession planning in grid operations is one of the industry's quiet ongoing challenges. The grid of 2030 will be built by decisions made in 2026. The investments in storage, in transmission, in smart grid infrastructure, in workforce development, all of them are being made or deferred right now. The machine that will exist in 4 years is already being assembled invisibly in the choices of today. It will be extraordinary. It already is.